When you ask a chatbot a question, the reply snaps onto your screen almost instantly. But beneath that fast response is a series of silent, mathematical transformations. A computer doesn't have eyes to read text, and it lacks any inherent understanding of letters. To teach these machines how to communicate, engineers feed them virtually the entire written internet. If they tried to store all those words in their original form, the physical server space required would be unsustainable. The text must be condensed into a much smaller footprint. But shrinking text down involves a trade-off. When you strip away the bulk of the data to make it fit into memory, you lose the specific context and definition that humans rely on. Whenever a machine condenses information for efficiency, it creates an informational void. The resulting data is useless noise unless the system preserves a specific structural map to reconstruct it later. Let's look at how this works with the phrase, "India is great." In standard computer formats, those 14 characters occupy a rigid, predictable amount of digital real estate. To save space, we need a way to represent them more efficiently. This chart shows the first step of the Huffman Data Compression Algorithm, frequency analysis. We count up the letters, and we can see that I and A appear most often, while letters like D and G only show up once. The algorithm uses those frequencies to build a hierarchy. The most common letters stay at the top of the hierarchy for fast retrieval, while rare letters are pushed down into the deepest branches. Now we use these branches to assign new codes. Because I and A are at the top, they are represented by shorter sequences of zeros and ones. The rare letters at the bottom require longer mathematical paths. When we pass the original phrase through this structure, the words disappear. What comes out the other side is a tightly packed string of raw binary math. We have successfully shrunk our text. Now imagine we take that tiny binary string and move it to a completely different computer system. When the receiving computer tries to open the file, it fails. It can't identify what it's looking at. This happens because raw ones and zeros have no internal meaning. By removing the letters to save space, we left behind a mathematical void. To read the file, the receiving computer must access the exact Huffman tree we used to create it. By tracing the paths through those specific branches, the system can decode the sequence back into the phrase, "India is great." This highlights a rule of data compression. Mathematical efficiency provides no benefit unless you permanently store the structural vocabulary alongside the data. The logic from that 1950s algorithm applies directly to modern artificial intelligence. While the scale involves billions of variables, the underlying mechanic is the same. When a large language model ingests billions of gigabytes of text, it cannot save raw words. The physical memory constraints are too tight. Instead, it uses tokens. A token is a numerical value created when the AI breaks human words into compressed mathematical representations. This tokenization process leaves the AI processing billions of numbers. This creates the same informational void we saw with our binary string. Without a way to translate those numbers back into concepts, an LLM is paralyzed. It cannot generate a single human word without an internal reference map. To function, every AI model must include a foundational token dictionary. This comparison shows how the logic scales. On the left is our simple Huffman tree. On the right is a massive, multi-layered network that translates complex vector numbers back into full paragraphs. This dictionary acts as the bridge. It takes the mathematical results of the model's internal calculations and converts them into readable human language. Storing this vocabulary is a physical tax on the hardware. It consumes a significant amount of active memory just to maintain that internal reference library, but it is a mandatory cost of the system. The intelligence of an AI system depends on its ability to process data, and that ability relies entirely on storing the precise vocabulary required to interpret that data.